thanks for having me out to give this virtual talk. Thanks for reaching out. I am an assistant professor at Rice University. I came out here from a postdoc at Stony Brook University and a PhD at Caltech, and I've been working for about 12 years now on Mars rover projects or Mars surface mission projects. I've worked on the Phoenix mission and the Mars exploration rovers, but the one that I'll be talking about the most today is Curiosity, or Mars Science Laboratory. And so we'll dig into some of the story of that. Right now, as I said, I'm an assistant professor at Rice, and I have a group in the geology department, the Earth, Environmental, and Planetary Sciences department, and we're working on understanding sedimentary geology in these ancient rocks that Curiosity has visited and across Mars. So I will get started. I wanted to start with kind of stepping back in the big picture and thinking about Mars. We've certainly approached our study of Mars in a different way than we have of Earth, and that's obviously because we're here. And for a long time, you know, Mars was just a dot in the sky. But we have studied Mars for thousands of years, right? The ancient Egyptians mapped out Mars's tracks. As soon as we could develop telescopes, they could show us the surface of Mars. Surface geologic type maps of Mars were produced. One of the first published map of Mars was an 1877 map by an Italian astronomer named Schiaparelli. And this is his map. And you'll notice he captured at least some major features that we still see on Mars today. The northern hemisphere is quite different than the southern hemisphere. And there are significant kind of channels through the middle here. But
are you sharing your screen?
Well, I thought I was.
I don't think, unless I'm just not seeing it.
Troy, I see it.
Okay, y'all can see it? Okay, I just can't see it as the host. Yeah. Okay, good. Just making sure. Okay.
Good. So you see, yeah, so this map he drew out, and what you see are, though, a lot of straight lines kind of crisscrossing the planet. And he was Italian, he called these canali, indicating that they were some kind of channels. Now, when that reached over to England, they were in the middle of their canal digging phase, right? You're right around the time of William Smith. You're right in that time when they're digging canals across England in order to transport goods. And so when they saw this map of Mars, they thought there must be an extremely intelligent society over there that is already transporting goods effectively across the entire planet. We can see their canals from space. And so this started some of that initial movement towards thinking Mars had these really intelligent civilizations. And then we kept imaging Mars through the telescope years. And so we actually retained some of those lines, although I'll point out nobody knows exactly what he was mapping out. I don't know if they were scratches in his telescope or his eyelashes, but those crisscrossing lines are not found on Mars. But the telescope images in kind of the decades preceding the space age kind of reinforce this story. And that's because as we imaged Mars through the decades, we saw different patches that were dark and light, and they would alternate through different years. We know today these are due to global dust storms that happen on a approximately decadal timescale that really go across the entire globe of Mars and cause these kind of light appearing patches to cover up these darker areas, which are basically dust-free or have less dust. So for a long time, you know, we were thinking of Mars in this kind of what we now recognize as totally science fiction-based way of having these strong, intelligent life forms and complex communities. And so with that in context, when we first actually got images of Mars in the 1960s, the Mariner missions flew by, we were incredibly disappointed when we saw that the surface was really ancient. The surface was covered in craters. It looked more like the surface of the moon than the surface of Earth. And those craters we know accumulate over long periods of time. So we could pretty quickly tell that these surfaces were quite ancient. And some of the first images sent back from that flyby. I love this quote from the press release, that man's first close-up look at Mars had revealed the scientifically startling fact that at least part of its surface is covered with large craters. Right? This is we came at Mars from a very different perspective, and we're just we've been surprised almost every time we've figured out something new about Mars. It's just always defying exactly what our expectations are. But so we recognized it's really ancient, it was cratered, it looked like the moon, but luckily we did a few more flyby missions, and the Mariner 9 mission was the first to really capture what looked like a channel. And so this was our first impression that maybe in the past, Mars was different. So maybe a lot of the surfaces are ancient and they're old, but in the past, it looks like there was some water flowing across the surface. We kept going. We went with the Viking missions. We were still looking for signs of life, even though at this point we knew that Mars looked pretty old. With the Viking orbiters, we finally surrounded Mars. We covered Mars with color imagery, and we're able to see that indeed it's dry and barren and looks mostly like the moon. But there are patches of water ice and CO2 ice, right? The North Pole and the South Pole of Mars have both water ice and CO2 ice seasonally. It's actually quite a lot of ice. The amount of ice there, if you were to melt it and spread it around Mars, would be about 20 meters thick all around Mars. So there is actually significant water ice still on Mars today. But the majority of Mars is dry, and the atmospheric pressure is so low that liquid water is not stable. And so you really are only dealing with that ice phase and a little tiny bit of a gas phase. And some of the other notable things are that volcanoes were active for a long time in Mars past. Some of them grew to be quite large. This is Olympus Mons, which is about 3 times the height of Everest. And that's one indicator among others that Mars actually didn't have plate tectonics. So the surface wasn't shifting around. You don't have subduction. You don't have any indication that the surface really ever changed. Instead, this is basically the surface from something like 4.2 billion years, just covered in different volcanic episodes, altered by aeolian, by wind that moves a lot of sediment around. And in the past, it's pretty clear that there was water flowing across the surface. So we see all different sizes, all different scales of large channels crossing Mars, going down into kind of the northern lowlands. We see some that look, this is actually one of the best examples on Mars of a valley network that looks like a precipitation-driven network that we see on Earth. A lot of other ones are these kind of major flood channels. But it's pretty clear that water was flowing across the surface at some time in the past. And so at this point, we were pretty sure that, water flowed across the surface, and there was a time when Mars was more interesting. But with the Viking missions, we couldn't find a good landing site. Both of the landing sites we looked at were pretty much covered in volcanic rocks, even though we went downstream in one of these channels. And what the problem with not having plate tectonics is that you don't get the same chance to re-expose ancient strata. And so we had to think about how would we actually go about finding stacks of layered rocks on Mars if all of the layered rocks are all of the strata, all of the ends of the rivers are just accumulating in these large basins, and we don't have a way to dig, and there aren't plate tectonics to lift those layers back up for us. We could see in a few places, though, indicators that we might be able to see some of the layered strata. And I'm going to show you probably one of the key examples that we found around the year 2000. So this was actually a couple decades later. So this is part of a system of craters that were partially flooded by some of these big channels. This large crater is called Holden. There's a river, comes into Holden, comes out up the top out here. That river loops around into this much older crater. This crater outlined with the gray circle is called Eberswalde. And you can see Eberswalde is actually older than Holden because the Holden ejecta crossed into Eberswalde. But I'm going to zoom in right here, and this is where the river that it came right out of the top, it breached the crater wall of Holden, looped around up here, and you can see part of the channel coming in right here. And I'll zoom in on that white box. And what we see here are delta deposits, but in inverted form. And so the river was coming in up at the top. You can actually see these nice lateral migration features of these channels that were coming down into Eberswalde crater. And so Eberswalde at that time must have held a lake, and the river coming in was dumping sediment. The interesting thing is that we can actually see those layers. So the sedimentary rocks were cemented, they were preserved and lithified, and then the wind must have blown enough. This is likely all aeolian erosion, but the wind blew enough to blow all of the fine sediments out of this crater and leave us with the coarse sediments that would have come in with the rivers in that flood. And so we can actually see the delta deposits in this inverted topography. And that means that if we land a rover over here, we do get to climb through sedimentary rocks and read the story of ancient strata, right? We can actually read the story of ancient Mars. We just have to find places where the wind helped us out. And so this was kind of revolutionary. So this was around 2000. Some of the next missions went to a couple different sites, but I'll talk about how we used this kind of trick to look for a landing site for Curiosity. Overall, one point I wanted to make was that overall this kind of tells us that we actually do have an ancient record on Mars. And if we look at a timeline, this kind of points out one of the things that I think is actually most exciting about being able to study Mars, is that as we've looked at Earth, right, I told you we have just a very different perspective. We started from the ground up on Earth, and on Mars we came from the sky down. But on Earth, we also work with a planet that's constantly changing. There's plate tectonics, there's life, there's water, there's hydrosphere. So most of Earth's surface is from the last billion years or so, right? And we do have some ancient rocks, right? We have rocks as old as 4 billion years, but it gets really hard to understand what the Archean looked like, right? It's actually very difficult to figure out when life started, because we have all these arguments about whether or not we've discovered fossils from 3 billion or 3.8 billion years ago or older. And those rocks tend to not be very well preserved. Well, the interesting thing is Mars actually presents an opportunity where that time period that would have been in the Archean on Earth actually comprises most of Mars' surface, right? So most of Mars' surface is from this time between 3 and 4 billion years ago. And at that time, it's quite possible that Earth and Mars looked really similar, right? And we think that that's, we know that's around the time when life started. We wonder what Earth was like at that time. We don't fully know what the atmosphere was like. We don't fully know how all of the geological systems worked in the absence of life, and potentially in the absence of plate tectonics. We're just trying to reconstruct that early Earth story. And Mars gives us a really interesting opportunity to look at what the record of solar system bodies was at that time, what geologic systems look like in the absence of life, and also what it could have looked like on Earth if we had slid out of the habitable zone early on, right? And so on Mars, we look at the most ancient surfaces. Those have clays, and by that I mean phyllosilicate minerals, right? Hydrated, looks like there is a lot of water present. When we get to closer to 3 billion years, we're seeing a lot of salts, mostly sulfate salts as opposed to carbonate salts that we see on Earth. But it does seem that a lot of the water was drying up. And since about 3 billion years ago, it's been mostly dry. And you've just had that wind blowing, which just the wind, but the wind has been quite powerful over 3 billion years of blowing across Mars. So with that, we think of Earth and Mars as very different today, but I like this little artist's impression of, what would have looked like 4 billion years ago. And at that point, it's much more possible that Earth and Mars were quite similar. And if you want to read more about this idea of using space to understand different time periods on Earth, we just put together a review paper this year called Probing Space to Understand Earth, and a little plug for that. Okay. So then we've looked across ancient Mars. We know how to see these rocks that have been exposed, and that you can actually kind of find those sedimentary layers. And the key is to look for areas that the wind has been blowing material out of. And so the landing site we selected for Curiosity was called Gale Crater. It's very close to the equator. It's about 155 kilometers across, or 110 miles across. It's fairly large impactor, and so that impactor actually caused the surface to rebound in the middle, and so this pointy, we call them boulder forming set of rocks right in the middle of the crater are actually a central peak that is quite high. It formed when the impactor actually caused a rebound in the rocks that it hit. And after that central peak formed, it looks like a lot of this crater filled up with river sediments, with wind-blown sediments, possibly with volcanic sediments. But then at some point, the wind changed and has since eroded out a lot of the material that was surrounding, or that was filling the crater originally. And the way we can tell is because some of the material that filled the crater is stuck to this central peak. And so this, we call it Mount Sharp, and you can actually see the layers in Mount Sharp right over here and that are stacked up. And those are all layers that have been exposed by the wind since the crater was filled. Now, that process is actually still occurring today, which makes this a particularly interesting site because what you can see is this dark sand. The dark sand is blowing in, the wind is blowing from this direction, and the dark sand gets pushed around the mountain, around Mount Sharp. These are active sand dunes right here. It accumulates in the back of the crater, and actually there's a tail of those dark sands going outside of the crater, out the back. And so this process of evacuating this crater is actually still occurring and exposing these sediments. And the exciting thing about this particular set of sediments was that when we went over it with a spectrometer, with one of our orbiting spacecraft, we were able to see that the lowest layers of the sediments contain phyllosilicate clays. Several of these stacks right in here are really rich in sulfate salts, which are the kind of one of the main salts that we see around Mars from that time period, about 3.5 to 3 billion years ago. And then there's kind of an unconformity that sits right here. And above the unconformity, we just see dry iron oxide, rusty dust, just like covers all of Mars today. And so the exciting thing was that we have one stack of sediments that actually includes all of these key layers through time that kind of represent our major geological, mineralogical eras on Mars. So with this crater as our destination, we sent the Curiosity rover. Curiosity is like the size of a small SUV. So think of it filling a parking spot. It's got 11 different scientific instruments. A couple of them that I'll point out, it's got quite a few cameras. The exciting one that's highlighted in this artist's rendition is a laser. The ChemCam is a laser that does a laser-induced breakdown spectroscopy. So it can zap rocks from about 7 to 20 feet away into a plasma, and then it looks at the spectrum of light that's emitted by the plasma to tell you what the composition of the rocks are. This is called the Mars Science Laboratory because it also has relatively high-tech laboratory instruments on board. And so what we can do is this arm extends out from the rover. It can actually drill or scoop. It can scoop into sand or drill into rock, collect a sample, and then deliver it to two onboard instruments. We have both a mass spec and an XRD. And so with this rover, we can actually do pretty detailed analyses of the materials that we find on Mars to tell what the mineralogy is, what volatile content is, et cetera. And I'll kind of show some of those examples. It takes about 8.5 months to get to Mars. And once you launch off Earth, you're still orbiting the sun. So you actually go kind of halfway around the sun to impact Mars at just this precise point that you've picked out on the surface. And the engineering of that is really amazing. And so I'm going to try, hopefully, you'll have to tell me if the sound works. If you can see just a brief video from the landing night. So this was August 5th, 2012. Can you hear sound?
Yes.
They look good. Or concentrator base. At this time, it will begin pressurizing the crusher system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. start of guided entry. We're navigating to feel the atmosphere as we go in here. The vehicle is just reported via tone that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. That is starting its first negative version. Reporting that we are seeing G's on the order of 11 to 12 Gs. Commercial 2 is starting. We are now getting telemetry from Oxy. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Feed has separated, but we're counting the ground expanse. We're down to 90 meters per second at an altitude of 6.5 kilometers per second. Standing by for batch separation. We are in powered flight. We're at altitude of 1 kilometer per second. Standing by for sky crane. Sky crane is started. You remain strong. Shaft confirmed. You're safe on Mars.
Given that I was, waiting at the start of my PhD, hoping this would land so that I would be able to finish my PhD, there's still palpable relief when it lands at the end of this video. But it was really exciting, just truly amazing engineering. This image is a real capture. So we had 2 NASA satellites orbiting Mars at that time, and one of them was acting as an immediate relay back to Earth to tell us what was happening, and the other one captured this picture of Curiosity dangling from its parachute as it was landing, right? And then the next stage of landing after the parachute was the sky crane, and the sky crane was this thing that carries a lot of the fuel and actually has jet packs that slowly lower Curiosity to the surface on a tether, and then that tether connection breaks and the sky crane flies away and crashes. And this is an image of the ground taken from the base of the Curiosity as it was being lowered from the sky crane. And the image shows the dust being blasted off from the surface, and you see this really big blast of dust on one side and a much smaller blast on the other side. And that's because the sky crane was actually adapting to the wind on Mars that day and trying to make sure that it cut the horizontal velocity by slightly tilting so that Curiosity would be set down evenly on the surface. And so, yeah, the engineering of this was absolutely amazing. It was a perfect landing. And we got to start investigating. And those guys in the blue shirts in the movie were all the people that worked on the landing and all the people that worked on Curiosity to that point. And essentially that night, the night of August 5th, 2012, they hand over the keys to the rover once the rover lands to the science and engineering teams that actually operated on the surface. And so this is a picture from that from a couple years after. I think this is the Mars Science Laboratory, the science team. And so we are scientists and engineers from all over the world at a variety of universities and different institutions that help work together to help decide what the rover will do and to interpret the data as it comes back. A lot of the data from the rover, especially pictures, are available to the public at the same rate as they're available to the science team. But some of the data requires a little more processing, and that'll be released to the public within weeks or months of acquisition on Mars. And then we'll try to write up the scientific papers, sharing that data and sharing the findings so that this all gets out into the world in many ways. And it's really been just so much fun to be able to work with these teams. It's very interdisciplinary. You have to learn how to communicate your science in a way that will help argue to the atmospheric scientists why geochemistry is important, or argue to the geologists why atmospheric science is important. But it's a really fun group to work with. Somewhere here, I'm in the middle in orange. There we go. And so the keys get handed over to us right after landing, and we immediately go take pictures of the mountain that we're heading towards. And these were some of the first pictures returned of Mount Sharp from the ground on Mars. And so it was just beautiful, right? You can see the whole mountain here. This requires an array of images. Each image is pretty small, but we make them into a mosaic. And then we do a color correction. So the sky isn't blue on Mars, but we do a white balancing correction that makes it so that the colors are the same colors that we would see if this outcrop were on Earth. And so when we do that, that's what kind of makes the sky bluish. Otherwise, it's just a sort of hazy reddish. And what you see are these dark sand. These are the sand dunes that are going around the mountain. And we can actually zoom in on some of the layers here and see this trough is where a lot of the clay detections were from orbit. These really nice, even flat layers are the salt-rich layers, mostly sulfates. And then this dotted line shows the unconformity, above which we mostly see this dry, rusty dust and anhydrous iron oxides. So seeing this picture, we were so excited. We're down on the ground. This is an orbital view of our landing site. That's where we blasted all the dust away with the sky crane. This is the way towards the mountain that we just took the picture of. And we're driving a car with 400 people from around the world. And there are no roads. And so you have to decide on a day-to-day basis which direction to drive in with 400 people. And probably the only time we decided semi-unanimously was this first section. And what we did was we drove this way, which was kind of the opposite of the direction we were originally thinking. This is actually a picture with Curiosity in it. So there's the rover. You can actually sort of see its little wheels in this light-toned outcrop. And so this light-toned outcrop actually represents the lowest point within this crater. So we saw the layers in the crater. And if you're studying sedimentary rocks, you want to start with the beginning of the story. And so we wanted to start with the lowest strata, and we also know that water flows downhill even on Mars. So if there was any chance for finding water, then maybe these light-toned flat deposits right at the base of this section would kind of give us a good head start on that. So then we drove over there. In the process, actually really close to where the dust was removed, one of the first outcrops we saw was this conglomerate. We were absolutely thrilled. We hadn't found real evidence for water flowing. There was some cross stratification we saw with the opportunity, but these conglomerates, right? These pebbles that are centimeter scale, rounded pebbles cemented together into a sedimentary rock, was kind of the first strong evidence for significant water from the ground on Mars. So we're heading in the right direction. We're seeing these conglomerates. We saw cross stratification from fluvial deposits. So these are kind of coarse-grained sands. And we saw some of this beautiful cross stratification as we're crossing over to that light-toned layer. And when we got down to the light-toned layer, That was the sheepbed mudstone, which kind of gives away what we found. We immediately pulled out all of the rover instrumentation. This was our first drill site. So we both used the instruments that we're able to use as we're driving for non-contact or brief stops. That includes the laser that I pointed out, or that I showed earlier with the artist rendition, right? But that laser just zaps very tiny spots on the rock, about 300 microns across, and gives you a sense of what they're made out of. It's semi-quantitative laser-induced breakdown spectroscopy. We also have an XRF and fluorescence instrument, and so that gives us kind of these spots about the size of a penny. It gives you the bulk surface composition of what's at the surface within that spot. And so we use those two instruments. We use this one as a survey tool, and then we use this one for slightly higher resolution or bulk compositions whenever we can stop and pull out the rover arm and actually put it down on the rock. But then just every now and then we get to drill into the rock. These drill holes are about 5 centimeters deep. Our first one was in that sheepbed mudstone, and the first one is this one. We do a little test hole, and then this is the real drill hole. And we were so excited right when we saw that picture because Mars wasn't red. As soon as we saw that there was some non-oxidized or material with iron that was not in an oxidized state just right underneath the surface, we were really excited already, right? And looking for these kind of habitable environments, or looking for preservation of organics, right? These reduced materials and reduced materials next to oxidized materials are great for, providing energy to microbes, and reduced materials can kind of better preserve those systems. So right beneath the surface, it's reduced. That's probably because the wind is actually still eroding out this area. When we put that into our XRD, this is how our XRD works. Instead of rotating the X-ray source, we actually rotate the powder, that's the drilled powder from the drill site, and let the X-rays bounce off the powder as it's moving. So our XRD patterns are these kind of cool circular things that we then integrate over the circle to figure out kind of a typical 2 theta pattern. But for those of you who have worked with XRDs before, this strong reflection at low 2 theta is indicative of phyllosilicates, right? Those are the layers in between the clay minerals. And this sample ended up being about 20 or 30% phyllosilicate clays. So then we heated it up with the mass spec, and we could see that indeed there were multiple redox forms of sulfur as well as iron, and there was a significant water release from those phyllosilicates, carbon dioxide and oxygen as well. So this was absolutely kind of, I always go back to this story of right at the beginning of the mission because within about 2 years about a year of landing, right, we made it over to this site and found a place on Mars that's about 3.5 billion years old and would have been a habitable lake for Earth-like life. This really kind of pushed us to view Mars in a way where we can actually do all the things that I said in the introduction. Right now, we're seeing Mars as a place where we can compare what was the surface like at the time when we think life started on Earth, and it could have started on Mars or it could have not started on Mars, but in either case, this gives us an example of what geology looks like in the absence of life and what it might have looked like right when life was starting, right? This is a completely habitable environment. It's a lake that was sitting at the surface. Again, we have those kind of reduced things probably because this is an actively eroding area. And so this sandstone ledge is retreating. And so these areas have probably only actually been exposed for tens of millions of years. And so these were really exciting samples. I want to say habitable. Okay, habitable for us is defined as, right, it's a very controversial topic, what habitable means. There's got to be liquid water. That liquid water has to be a relatively low pH, temperate water, right? Low pH, not super salty, not acidic, not basic, not super salty, kind of neutral zone water. There has to be all of the ingredients for life, so all the elements You have to have all of that for an extended period of time. Here we found about 1.5 meters of strata of mudstones that look pretty continuous. So we were saying tens of thousands of years, 10,000 years maybe. And you have to have energetic, or you have to have some source of energy, which in this case, we said the redox conditions would have provided some energy for microbes had they been there. Now, one of the exciting things that came out of this site, actually a couple of years later, when we finally had time to get through all of the details of the mass spec samples, we drilled 2 spots here. So the John Klein sample was right over here. Another sample was called Cumberland, and it was a little closer to the ridge. And in analyzing the Cumberland mass spectrometry results, in 2018, there was a new paper that showed that there were organic molecules preserved in this lake. What we think is there is kind of a sulfonated kerogen molecule, some kind of large molecule that we can't fully differentiate, right? Because we're only heating it up at low temperatures. But what we saw was a wide variety of kind of small carbon-based, small organic particles, most of which contained sulfur as well, that we think broke off of a larger kerogen-like structure. To me, the really exciting part of this discovery was that if there was life on ancient Mars, we have now reason to believe it would have been preserved. We don't know if this particular molecule was biogenic. You can also have kerogen come in on meteorites, or you can have it in volcanic particles, but in any case, we know that this lake contained organic molecules and that some of them were preserved through time. And in fact, that one of our first 2 drill holes on Mars found organics from 3.5 billion years ago, which, if you know, studying the Archean or studying the Neoproterozoic and trying to find organic molecules, to find indigenous organic molecules that quickly is really amazing. And so this site is always just one that we really emphasize as quite exciting. Okay, so after we moved on from there, our goal is to climb up these layers of the mountain and see kind of where the environment went from there. So at one point we have a habitable lake. What happens next? We climbed back up on the sandstone. We tried to kind of book it towards the layers of the mountain. They were just beautiful. You can see it's naturally appealing. So we tried to drive as fast as we could. Now, driving as fast as we can is like 100 meters a day, but we're driving and we're letting the robot kind of decide what's the fastest path. It was a couple months before we took a image with the arm, where we actually had the arm under the rover and took an image of our own wheels. And we were pretty shocked when it came back looking like this. We were not expecting to see Mars through this part of the wheel. And so what we realized was that the active erosion at this site has left a lot of ventifacted sharp rocks at the surface. And so everything has been eroded into pointy rocks scattered across the surface that were just popping through our wheels and scratching them up. We had a big powwow, a team meeting, a discussion of, what can we do to minimize the damage to the wheels. We stopped driving for a little while. We had a bunch of people analyze it. The thing is, it's a car on Mars. You can't take it to the mechanic. You can't do anything. All you can do is minimize future damage and hope that this won't be the first thing to go. Can't guarantee what'll happen, but they did kind of find a way to say this will keep breaking, but it probably won't be the first thing to die as long as we, follow these precautions. So we started driving slightly differently after that.
What were the wheels made out of?
They're aluminum, and it's actually really thin. So that comes across as embarrassing when we say it now, that it's only about like 2 or 3 soda cans thick. But the goal at the time was to have the largest surface area on the ground we could. We've had previous missions that all gotten stuck in sand. We're hoping to have the largest surface area so that we could get out of sand traps and the lightest wheels And we needed to make sure that they were resistant to that landing, which could be kind of hard even with the sky crane, but they survived that just fine. It was just that these pointy rocks were sharper than we thought. One feature, these holes are actually supposed to be on the wheels. You can see as JPL was designing the wheels, they wanted one part of the wheel to be different so that if you look back at the wheel tracks, you can see that kind of different marker every one rotation of the wheels and say, oh, we've come, it's just another way to check how far you've come. JPL originally wanted it to say JPL, so that if you looked across Mars, it would say JPL, JPL, JPL. And NASA said you can't brand Mars. It's not yours. You're gonna have to put something else. They put these holes in, and as soon as Curiosity launched, as soon as it's on its way to Mars, they did a press release saying this is JPL in Morse code. So that's one. So there are some holes intentionally there. These ones were unintentional. We put together, I said we put together our Tiger team, and this is just one slide from an actual presentation around that time, where we asked 5 experts in, how do we interact safely with the terrain and get the safest way from point A to point B. I don't know if you can see this on your screen, but there's probably about 8 paths. I don't know how we ended up with so many more than the number of path planners. And so this is really a challenge every day, right? You're working with, again, 400 people driving one car. We always have to make compromises and have to explain, exactly what our reasoning is for whichever direction we're going to go. And we ended up kind of following this pink path, actually, which is kind of out of the way, but covers a lot of interesting views and mostly avoids strong sound traps. Here are some of those views. These are some of the rocks that we came across that were kind of the most indicative of what we were looking at. We were continuing to see some conglomerates, some sandstones with cross stratification, but this section was really nice. So this is kind of a side view, and then if you were to sit the rover right over here and look back this direction, you'd have this image. So this is looking head on at these layers. And I don't know if you can kind of start to see, they're all dipping towards the middle of the crater. So this is some kind of a feature river that's coming in from the rim of the crater. And what you're seeing are these little deltas. So we were approaching lake sediments in this direction towards the central peak. But at this point, we were seeing kind of some of these little cliniforms, essentially, of these rivers actually depositing sediment and so reaching the lake. So this was a really cool deposit. And, as we continued this way, we did eventually get to those lake deposits. We had been really excited with the 1.5 meters of stratigraphy in the sheepbed mudstone. We got here, this is called the Murray mudstone. We're now at about 370 meters of Murray mudstone. There's some sections, mostly near the base, with thicker lamination. So these are about centimeter thick laminae, centimeter scale laminae. Most sections have millimeter scale laminae, but this is just beautiful, flat, calm lake, right? You just had this lake. We don't know if it really filled the whole crater, but at least in this region we're driving through, there was a lake for probably a really long time, and most of it is this beautiful laminated mudstone. It's just a very calm lake. We see some sections with some cross stratification or hummocky cross stratification, different things, but for the most part, we've just been amazed that this kind of environment would have been present on the surface of Mars for, at this point, we're talking hundreds of thousands, millions, tens of millions of years, which we've kicked back to the climate people because we haven't figured out how Mars was warm enough for that. But just to give you, this is a terribly vertically exaggerated figure, so don't let that totally fool you. But the Bradbury group is where we saw the river sediments. That little dip in elevation versus distance the rover has traversed is the mudstone we went to first. So then we just saw all those little cliniforms. We saw these rivers coming towards the middle of the crater. And since we've been climbing up the mountain in the middle of the crater, we've been on this Murray Formation. I have a couple ways to show kind of our whole picture geology. I'm going to start with a little video that I'll just talk over. So you've got the surface 4 billion years ago. At about 3.8 billion years ago, there's a really large impactor that creates the central peak and Gale crater. Then you have water that starts to come in. Some of that could have been hydrothermal or groundwater, but you definitely also had water flowing in from the rim of the crater. That water is carrying your conglomerates, your sandstones, and your extensive layered laminated mudstones, right? And it lasts for a really long time. So you build up these deposits. Eventually that water does turn off. We don't think all of the mound was fluvial. This part was probably Aeolian. So you have some kind of wind-blown system that fills up a lot more of the crater. And then the wind changes. At some point, the wind totally changes and starts eroding material out of the crater. And it doesn't just erode the wind-blown material, right? It actually erodes into the sandstones and conglomerates and mudstones, leaving that moat around the crater that exists today. We know that there were multiple stages after that of fluids coming through and fracturing the materials that had been, or multiple stages of fluids coming through, and then you get to 2012 and we've got the rover there ready to investigate, right? So those are the layers we've been driving through, are those conglomerates, those sandstones, and then the mudstone. And like I said, we've now been driving for quite a bit through mudstone.
We had a couple of questions from Ken Williams.
Yeah.
Ken, you want to just ask them yourself, or? Maybe he doesn't have sound. Basically, he said, are the thin layers yearly or daily layers? And then are they cyclic, and what is the cycle length?
It's a great question, and one that I think we frequently ask on Earth as well, right? The kind of idea of these varves, or of something where you would say varves, right? We actually avoid that because that implies annual. But whether they're seasonal layers, annual layers, or flood event layers, we're not sure. They're very steady in thickness in different sections. I don't think varves is a bad interpretation, but we just don't have a time constraint very well. We've been able to date just a couple of things using kind of potassium argon dating and helium dating with our mass spec, although it's low resolution. But that has told us that the detritus coming into the crater was around 4.1 billion years old. And some of the last water events and fractures were up to 2.1 billion years ago, which was actually shockingly recent on Mars. But we don't have good dates to constrain what those layers, the timing that those layers represent. Oops. So one other way to look at this is up towards the top would be the edge of the crater. This is climbing up the mountain, so this is uphill. This yellow line represents our rover track, and I'll show this with a little more. And these are the sand dunes that have accumulated at the base. And so here's some of the main units we've seen, right? Out here were the river, the fluvial deltaic sandstones. The majority of this has been laminated Murray mudstone. We crossed a ridge line that we thought would be a distinct depositional environment, but turned out to be mostly a diagenetic feature, where there was enhanced erosion and enhanced hematite visibility from orbital signals, although probably about the same amount of hematite as some of the lower sections. And then this is a trough where we detected clays from orbit, although we've since learned that almost all of this material had significant clay. And I'll zoom in this red star, and this yellow dot is where we are right now. So that's where we are today in this clay unit. These are unconformable Aeolian sandstones that actually appear up here as well. And it looks like at least once after the original deposition and erosion sequence that I showed in the video, there was at least one more time when enough sand came in and then was later cemented, that there's actually kind of an unconformable layer pasted on top that would have represented a time with a lot more sand that actually got cemented onto some of these layers. And it's kind of pasted on over here and right up here. Now in this trough right here, we have some images of Curiosity driving across. So this is the ridge and this is the trough. Right up here was about close to a year ago now, and over here just a couple months ago. So this was this red star that I pointed at. So from the red star, you can see we're actually still in that clay. We're still in the laminated mudstone. We've got another drill hole right here. You can see it's actually still gray. So we're still in a habitable type environment. And you can see some of those sandstones that are pasted on top of the mudstone, unconformably overlaying those lacustrine units. Plus you can see a selfie of the rover, which we always like to see. It's still doing well, a little dustier for the 8 years on Mars. This is a panorama it took from that site. You can see the tracks across the surface. There's another exposure of the capping unit. This is actually the moat around the crater, and then what appear to be mountains in the background are the rim of the crater, which again are 4 or 5 kilometers tall at that location. So these are, and also about 30 or 40 kilometers away. So you actually have pretty good visibility to see those kind of layers. We have taken drill holes as much as we could as we climbed, and the variety of kind of colors that you see here starts to tell you that there have been a couple of zones with different diagenetic events, more hematite, more magnetite. Some of these redox conditions have shifted through the lake sediments, but for the most part, these are all represent environments that would have been habitable, and a couple of them actually mostly at the base. Cumberland and Mojave were the ones with the strongest organic signatures right at the base. And then we were hoping to find some of that in the clay unit. We're still drilling in the clay unit right now, but this whole set of samples on the bottom row are samples that we've drilled in the clay unit. Clay unit was something we named it from orbit because from orbit we detected clays. In reality, there were clays everywhere, but dust obscures our orbital detections. Okay, so I just want to do a brief thing about some of the projects my lab group has been working on with these data, and then what's coming up next on Mars. So my lab group, we're mostly working on sedimentary geochemistry and trying to understand those sedimentary rocks from source to sink. You guys know about this, right? So we've got the source rocks, the provenance on Mars. This is about 4.1, 4.2 billion years old, mostly volcanic. We thought it would have been all basaltic. We're starting to learn that some of the volcanism would have been a little more complex than we thought. As those particles get carried into the rivers and into the lake, there was actually very significant transport sorting of different mineral grains, and I'll show you why on the next slide. And then trying to disentangle, what kind of weathering was happening at the surface versus what's happened in diagenetic events later. What's cemented these rocks, kind of what can we say about the paleoclimate versus the cement versus groundwater episodes that happened later. Unfortunately, we have to try to disentangle all of that without any thin sections, which really is probably the first thing I would do if I got a sample back from Mars, is make a thin section, because it would be amazing. It would be very helpful for this work. In the absence of thin sections, every now and then we get lucky and find a really helpful rock. This rock we named Harrison. It's about a fist-sized rock that was in a conglomerate in the river. And what you can see are these huge plagioclase phenocrysts stacked up against each other in a basaltic ground mass. And this kind of clinched the story that a lot of the rocks that were carried by these rivers had really significant grain size differences in the original minerals. And so a lot of the chemical differences we saw were probably related to just when these rocks were breaking up, all of these plagioclase minerals were much more coarser grained. And so a lot of the geochemical differences we were seeing were really just sorting of plagioclase minerals into the coarsest grain fraction and mafic minerals into the finest grain fraction. So we saw a lot of linear trends with grain size. And so that we published a while ago. And then I've got a couple of postdocs now working on like the next step. Valerie Pire has been working on what formation process you can actually deduce for these igneous rocks because a lot of the igneous minerals are barely weathered. And so you can actually capture what were the igneous minerals being carried down here and what kind of volcanic process would be necessary to form those minerals. And what you might have gotten from the texture of this rock is that there was probably fractional crystallization. You probably had multiple episodes of fractional crystallization in the subsurface to produce these large phenocrysts and then erupt them. So we're not at least looking at a very simple basaltic system. There's at least one more step of complication in that. On the other side, another one of my postdocs, Mike Thorpe, is kind of working in between Rice and JSC. And he took a bunch of samples from Iceland and from Idaho in these basaltic rivers that are carrying, primary basaltic detritus from volcanic systems, and looked at how much weathering actually happens in the river and in the first depositional episodes. And if we compare this kind of indicator of weathering, this chemical index of alteration between Idaho and Iceland and what we're seeing on Mars, we're actually seeing that on Mars, you probably were in an environment that's a little colder than or equivalent to Iceland today. And so these were very cold rivers, or the sediment deposition was very rapid in the times when the rivers were flowing. So we're thinking of climates like Iceland when we're looking at ancient Mars. And just, I wanted to point at this, I said this yellow dot is where we are today. Here is an image of the surface that was actually taken on Mars yesterday. I told you images from Mars are released to the public as fast as they're released to us. So it's always fun for me to look up what was the most recent thing we saw and share it with whoever I get to speak with. What you see are some of those mudstones. You can see strong effects from the wind. A lot of this kind of lineation is from the wind blowing across the mudstone, and little pebbles and different things cause these wind tails. So there's a lot of ventifacts. And we're right beneath a cliff. Let me go back one. Nope. Right here, we're right beneath the cliff where there was Stimson up on top. And so that's probably what some of these float rocks kind of are falling down off that. You see the active sand with the ripples and the wheel tracks from the rover here as well. And this is the arm that's folded up against the rover for when we're driving. And the next step for Mars is the Perseverance rover. Our launch window starts in just barely over a month, so we are counting down. Perseverance is the same size as Curiosity, but does have better wheels. It does also have a different suite of instruments. It is not a science laboratory to drive around on the surface and do XRD and mass spec. Instead, the internal parts of Perseverance are mostly dedicated to sample holding. So what Perseverance will do, it does have some instruments. It still has a laser, just like Curiosity, and it still has analytical instruments on the end of the arm. But what it will do, its main purpose, is to drive around its landing site, which is another one of these inverted topography deltas. This is a Jezero crater. Here's the river coming in, the rim of the crater, this inverted topography delta right at the edge. So it'll land right around here, drive up to those delta layers, potentially drive out of the crater, we'll see, and collect samples. And so it's going to aim to collect something like 3 dozen pinky-sized samples, and it has a little mechanism for holding them on the inside of the rover. It'll drive around and collect those, and then leave that cache of samples on the ground on Mars in a nice little pile somewhere. Another mission will come from Earth, land on Mars, have a fetch rover that goes over and grabs the little pile of samples and brings it back to its landing base. At the landing base will be a unit that will actually launch from the surface of Mars with all the samples on board into orbit around Mars. Once it's in orbit around Mars, another satellite from Earth will come, grab that package of rocks from orbit around Mars. It won't have to land on Mars because it'll grab it in space and bring it back to Earth. And then I can have my thin section. Actually, probably not. It'll be way too expensive. But that is the goal. So that is our big plan for the next about 10 years. We're hoping to get those samples back right around 2030. I've heard optimistically 2028, somewhere in there, probably early 2030s, to get a variety of samples from Mars back to Earth so that we can properly analyze the organics, the thin sections, what is going on in the history of this planet. And so we're really excited for that launch next month. And yeah, so the Perseverance rover, Curiosity is still driving around. Curiosity will make it a little bit longer. Wheels probably won't be the first to go. The power source is decaying, so we've only got probably 3 or 4 more years on that. So that's where we stand. Thanks.
That's awesome.
Wow. So how did you actually get into studying Mars? Was it just by chance, or was this your lifelong dream?
It was mostly by chance. My lifelong dream switched several times. I wanted to be an actress, and then I wanted to be a biologist, and then I definitely wanted to be a chemist. And when I found geology, it was really the same way as a lot of you guys, right? I found geology in college, and just happened that the first job I kind of asked for with a professor was working with the Mars rovers, and the interdisciplinary team. I just love working on those interdisciplinary teams, helping operate the rovers. And so that was what really made me fall for it entirely. And then, I got lucky with the timing. Curiosity, we had Mars, Spirit, and Opportunity. We had Phoenix, and now we've got Curiosity. So we've just got so much data from Mars over the past decade to keep going through.
That's awesome.
In your present picture, there was a rock that looked like a meteorite. Is it possible that you had a meteorite lying on the surface beside you?
I think those ones actually, so this picture that I have up right now is from a totally different area, but you can see the mudstone and the sandstone cap rock, and you see where the sandstone cap rock is sliding down these chunks right onto the mudstone. I think that's what we're seeing in the picture from today. It's in a very similar environment where the Stimson is exposed. But we have seen meteorites on Mars, and the Opportunity rover in particular saw several different meteorites as it was traversing across these plains. And we stopped and pulled over and looked at a whole bunch of them, and eventually there was a lot of team drama about whether or not we were going to ever stop for another meteorite. But we have seen at least one with Curiosity as well.
In several of the earlier pictures, there were things that looked like fracture patterns in those mudstones. What's the cause for any sort of fracturing in the absence of tectonics?
Yeah.
Or are they something else?
So much of it is just related to like freeze thaw and probably pressure release in this area. We've seen, but there are fractures that cut through every unit we've seen on Mars. There's fractures visible from orbit. There's all sorts of scales of polygonal fractures in these units. Actually, again, this picture I've got up right now, you can see that the rocks kind of show up as flagstones almost, right, all across the terrain. And a lot of that is going to be the thermal hot cold. So between day and night, it's about 100 degrees temperature change. And then you can even have stronger seasonal changes. And so we think that's contributed a lot to the fracturing we see today. And the ancient fracturing is probably due to loading and unloading. We've seen some hydropressure fractures in a couple different locations. A lot of them are filled with calcium sulfate.
So you have some great pictures where Curiosity is in the photograph. Who took the picture?
So what you'll notice about this picture of Curiosity is that it is missing its arm. So here's the comparison with Perseverance where you've got the arm out. The camera on the end of the arm is designed for up-close pictures of rocks. It's called the Mars Hand Lens Imager. So it has a pretty small field of view. And so we have to extend the arm out really far and then use that to take these pictures. And it actually takes about 80 pictures with the arm at like all different contortions so that the arm's not in the picture to get the full picture of the rover and part of its surroundings. And so by the time we stitch all of those together really carefully, kind of avoiding the parts where the arm is in the picture, you end up with the rover with no arm But it does take a full day to take a selfie. So every time you see one of these rover selfies, it means we planned a full day on Mars to take it.
Dang it, I thought it was Marvin the Martian.
Yeah. Not this time.
We have a person asking if it is possible there were huge glaciers and fluvial patterns developed and melt from underneath the glacier, similar to Greenland.
So let's see. If there were huge glaciers in this crater, is it possible?
They didn't specifically say in their question.
So I think it is possible. We have been looking, especially because we had all those fine scale laminae, we really looked for any kind of a drop stone or any kind of indicators of glacial activity. And absence of evidence is always less satisfying than direct evidence. But we have not seen any indicators of glacial activity in this crater in these depositional layers. And because of that, we tend towards thinking that it was a lake in balance with the atmosphere, open system lake. The climate folks have we really struggle to come up with a way where Mars would have been warm enough for that long of a time to have liquid water sitting at the surface. 4 billion years ago, the sun was 75% as bright. Mars is 1.5 times as far from the sun as Earth is. So you need a much stronger greenhouse effect than we have on Earth today for Mars to have liquid water on its surface 4 billion years ago. So we're still trying to figure out what that atmosphere could have looked like. And so because of that, we're always right on the border of thinking, okay, is this all ice that we're looking at? But we just haven't seen any drop stones or clear glacial indicators in these lacustrine sediments. So we go back and forth. So we don't see clear evidence for glaciers though. So at this point, we're thinking more temperate. Slightly.
Kirsten, we were really happy you came to the HGS Scholarship Night when we had Jessica Watkins speak. When do you think she might be the first person on Mars?
I would love for Jessica Watkins to be the first person on Mars. There's a few steps we've got before we'll see people on Mars. So we've got to get those astronauts back to the moon. We have to figure out how to have a station there and live on the moon for a little while. And then we will probably want to launch from the moon to Mars. And so, step one, get people back on the moon. Love to see it be Jessica first. Love to see it be Jessica there, each of these stages. But we got to get people on the moon living there, and then we can look at going to Mars. The radiation environment is really challenging, and the duration of the trip is very challenging. It would be a very different mode of operation than we have with the International Space Station, where people on Earth can talk to the astronauts on a constant basis and help manage all of the systems. A trip to Mars would really be the astronauts out there on their own with maybe a 15-minute delay in signal one way, sending anything back to Earth.
Advice for recent grads who want to study space.
You can come into some of these Mars studies from a really wide variety of backgrounds. But as with a lot of other things, getting internships, talking to people, looking at PhD or research opportunities. The people working on these missions are spread out. I'm at Rice. We have a bunch of different universities across the U.S. and across Europe and Canada and Russia and so all over. And there are also research labs working on these projects. So there's kind of a lot of different avenues to approach working on Mars projects. For any given project, there's a whole new set of people because it depends on who's been developing the instruments and who's kind of applied to be on that particular mission.
Have you seen any evidence of periglacial formations, for instance, patterned ground?
Definitely near the poles of Mars. So where the Phoenix lander landed, there were all different scales of polygonal fractured ground that were based on, that were ice polygons.
Mm-hmm.
And so when we actually dug into the surface with Phoenix, we saw patches with nearly pure ground ice separated by troughs that had significant sediment deposited in them. and other areas that had kind of poor ice in the sediments. And so we saw kind of all varieties of those pattern grounds. Now that mission had to go up. That mission went up to, I think it was 60. It was quite high in latitude. I think something like 60. And so it was even higher than that. Anyway, so that one, the problem is you can only survive for the Mars summer. Mars seasons are twice as long as Earth seasons, so we made it for about 5 months before ice starts freezing to the ground. And in that case, our solar panels broke in half, and we could no longer communicate with it. So, so there is active polygonal patterned ground today, but it's up near the poles.
Thank you.
So
Go ahead.
once your Perseverance launches, how long does it take to actually get to Mars?
Again, about 8.5 or 9 months. I think it'll land in, did I put that on the slide? Oh, that didn't go in the right direction. Landing date is currently set for February 18th.
Okay.
It will depend a little bit, or it may not actually. It may not depend exactly on when the launch window. We get a 2-week launch window every 2 years to go to Mars. And so you gotta have the weather conditions right and everything else. You probably saw the recent launch to the ISS. So hopefully it launches in those 2 weeks, so we don't have to delay 2 years.
Oh, wow.
But it'll get to Mars in February.
Somebody asked about any concern about returning samples from Mars, and they asked about COVID-20. I guess it might be COVID-21, maybe. I don't know, COVID-30.
Yeah. So that's actually, I just was on this report, and it is kind of a fascinating tangled issue called planetary protection, where we have international treaties where we have all agreed not to contaminate potential life from other planets, and also not to use things from other planets to contaminate life on Earth. And so planetary protection was kind of codified in 1957, and we are still figuring out exactly what that means for things like sending people to Mars. If you send people to Mars and if there's any chance of extant life on the surface, do you then contaminate the extant life? And like, how can you constrain the landing site for humans in a way that would allow that potential life to survive, or the potential for astrobiological studies in the future? We need to be really careful since we've contaminated a lot of our own planet, right? Like you gotta figure out how to do that. And in the same vein, we have to be really careful bringing samples back from Mars. So a lot of the work that's gone into Perseverance has been in those sample tubes, making sure that they're totally clean and that they will be totally sealed and secure. And the next mission, when it grabs them, we'll put like another envelope around them, and the next mission will put, additional protection around them so that you don't have something that was on the Mars surface that crashes into Earth. Instead, everything from the Mars surface needs to be super contained when you land on Earth, and then you put it in quarantine, right? So whether or not it's a high risk definitely depends on your kind of personal views, but because it's an international treaty and because it is a risk, we're definitely doing a lot to work on that.
Okay. Let's see. Is it fair to interpret geologic features on Mars with Earth processes as a basis?
Yeah, good question. So we have to accommodate the different atmosphere, and we don't have a perfect understanding of what the atmosphere was like in the past. And we have to accommodate the different gravity. And we do have to be a little bit careful in terms of geochemistry and different things, where you can ask questions about everything, every process we spend a lot of time thinking about this. How would this process be the same or different on a different planet? Could lava flows have a different viscosity if they have more phosphorus? Could, rivers transport things differently in the absence of life? And there's a few things that we've found that are slightly different, but they've led us to interesting conclusions that have made us reevaluate our understanding of those processes on Earth, which is a really fun kind of twist on this planetary studies, right? When planetary studies lead us to reconsider how we've defined processes on Earth. maybe one of my favorites is this one, and this is a Lepotre science paper. These sand dunes on Mars, on Earth, you've got ripples and you've got dunes. So you've got 10 centimeter wavelength ripples approximately, and hundreds of meter wavelength dunes. On Mars, when we saw the active sand dunes, they also have sinuous crested 1.5 meter ripples. So we call these large Martian ripples. It's a different bed form than we see on Earth. And it turns out it's related to the low viscosity of the atmosphere. They're still working on all of the physics for it, but they form in a way that it's another aerodynamic process, kind of like more like dunes than like our regular ripples. And so in figuring out the physics of these large Martian ripples, we ended up with an endpoint for aerodynamic hydrodynamic ripples that helps us define the wavelength of subaqueous ripples on Earth, and kind of what conditions lead to different wavelengths. And it like kind of just slightly tweaked the equation. But it was a very unexpected finding that the atmospheric conditions on Mars would create additional subaerial bed forms that then could actually tell us about wavelengths expected for subaqueous bed forms on Earth. This type of bed form may also occur on Earth, but it turns out that in the Earth atmosphere conditions, these ripples would be 10 centimeters long. So they would actually be totally covered up by impact ripples on dunes. And so Earth conditions actually hid this feature from us.
Okay. How are the volcanic craters in Mars are similar or dissimilar to ones on Earth?
They actually are, they're very similar. You're looking at mostly basaltic, like is the stuff right around Gale. We're discovering there was a little bit of fractional crystallization, right? But on Earth, we've got stuff like that all the time. The volcanic craters are pretty similar. Some of the lava flows may have had a slightly different viscosity, higher iron content, but in general, it's very similar.
Then there were just a couple comments about the fact that we did return samples from the moon, and another note that we learned that tardigrades can survive space due to our space missions to the moon.
Yeah,
And that's all we've seen in the chat so far. With a lot of thank you and awesome job and claps and kudos and bravos and those kind of things.
oh, great. Yeah.
Any other questions? Well, we thank you so much for presenting for us. This was exceptional. I was recording. I hope the recording works. I haven't tried to do recordings on Zoom yet before, so I'm going to check it out and see. But if it does work, then we'll get it posted up to the HGS YouTube site and get that information out. I'll also work with the office to get certificates out for everybody on this presentation and on our meeting. I thank everybody for joining us tonight, and thank you once again for speaking and for bringing us this exciting news. We'll be looking forward to that launch date.
Yeah, thanks for having me. I'm definitely counting down myself. So
I bet. With that, we'll sign off.
Yeah, thanks so much. I appreciate it. Have a nice evening.
Thank you from Martin. Bye-bye.
thank you.
Thank you so much.
Thank you.